Indeed, I'm going to talk about Honeycrisp today. This is joint work with my great co-authors, Brett Hemingway Falk, Daniel Noble, and Andreas Haberlin. Modern phones, like the ones that probably all of us have in our pockets right now, often have predictive typing features. And these are going to suggest words based on what we've typed in the past and what we're likely to type in the future. So in this made-up example here I have on the screenshot, I've texted my friend about this talk, and it's going to pop up a few suggestions based on what will complete the sentence. So here's some possible adjectives that it could potentially suggest. Now, often these models are going to be stored locally on devices to allow for fast suggestions, but in practice, these are using models trained on lots and lots of user data. So our scenario looks something like this, where we have many devices who are all uploading information to one centralized party, which we're going to call the aggregator. And I'm going to use that word for the rest of the talk, but this could represent one of many large companies who has access to many devices like this. Now, every phone is going to collect numbers on how often certain words are typed, and that's going to help the aggregator with their models. So here's a toy example of two different words and the distribution in which different devices are typing these words. And the aggregator will take all of these vectors and take the average. So sum them up and divide by the number of users to get this total vector. And right off the bat, this raises privacy concerns, as was illustrated in the previous talk. So there's a lot of things that if I start typing this, I might not want the result to this to show up in somebody else's predictive text. And there's other things that I might never want to send in the clear to any aggregator. And in this scenario, what we see is that we get exact accuracy because the aggregator is learning exactly the frequency over all the words that people are typing, but of course, there's no consideration for privacy. Now, to use an example, so Apple is aware of this issue, of course, and so they have implemented a system using differential privacy. And there was some introduction to differential privacy in the talk before, and I'm not going to go into a lot of technical detail, but we can think about it as just adding some random noise to the data, or a little bit of random noise or imprecision. So in this example, I've now added some imprecision to each of those data points of the devices, and that imprecision is, of course, going to percolate into the aggregate vector. Now here we've guaranteed privacy, so with some official differentially private guarantee. However, adding this much imprecision at every single device gives us a substantial loss in accuracy. So differential privacy, it has become this gold standard in privacy mostly because it allows us to reason about things quantitatively, and it gives us these formal guarantees. But it introduces this privacy accuracy trade-off, which we can think of as some sort of tunable knob. And this tunable knob has, on this left side, small values of epsilon, in which we're going to be adding more noise. That intuitively means more privacy, but less accuracy. And on the right side, higher values of epsilon means less privacy and more accuracy. And there's a discussion in the literature about what to set epsilon, but a common value that often pops out is epsilon equals 1. And this is a privacy budget that should be set for the entirety of the system run. And once this privacy budget or privacy loss has been hit, the system should stop issuing responses to queries. And we see that in practice, Apple actually uses a value of epsilon equals 16 for all the data that they're collecting. And in fact, they renew this privacy budget every day. So they're permitting a daily privacy loss of 16. So this means that Apple has made a choice of parameters to prioritize accuracy for use in their models, but in doing so set this very weak epsilon value in terms of protecting privacy, which means that it could be very easy to learn almost anything about an individual's data. Now, I'm going to talk to you about the system that we built, which tries to address this privacy utility trade-off. So whereas Apple gives good accuracy, if we set epsilon to 1 with the same system, we get the flip side, so we get good privacy but sacrifice accuracy. And I'm going to show you how we can actually get the best of both worlds, so both the good privacy guarantee and reasonable accuracy. And I'm going to tell you the two key ideas that make this work. The first is leveraging this idea, sticking with our example of words, is that word distributions don't change very frequently. So here's an example of the graph of Google search trends of the word impeachment over the last year. So we can see that there's a long period of time in which this remains fairly static, and then we see some big spike in the data. So if the aggregator is trying to learn about the frequency of the search, they might kind of ask, is it still at 0? Yes. Is it still at 0? Yes. And they would ask this many times, and nothing is really changing. Until we get this one spike, in which someone is telling them, no, you should now update your guess. It's actually now 0.9. And so intuitively, we can kind of think about this as not really seeing any real privacy loss unless the data changes. So we're not learning very much because the aggregator already knew that the data was at 0. And what the sparse vector theorem, which has been around in the theory literature for a long time, lets us do is lets us reason about how much privacy loss this is, and lets us essentially guess using previous answers without charging our privacy budget significantly. Now, the only way this could work is if the system held the real answer somewhere to issue precise responses to the aggregator's queries. So if you wanted this to continue with the aggregator asking, we need that precise answer somewhere. So I'm going to show you how this mechanism is actually achieved. And one insight is that we're going to perform this over encrypted data. So in this scenario, all the users are going to have their same vectors, but they're going to encrypt them. And we're going to be using homomorphic encryption, which gives us the nice property that the sum of these encryptions will be preserved. So the aggregator can actually do this sum for us without ever seeing the data. And we're going to take this encrypted value and reveal it to the aggregator only when the result is different from their previous guess. And so this lets us allow the aggregator to still do most of the work, so they don't need users to work very hard, but they won't see the precise answers anymore. So in detail now, I'm going to run through this system. We still have the same group of devices here, and they each now have one data point. And we're going to choose a random set of these devices that pop up in orange. I hope you can see that. And these are going to perform some small multi-party computation in which they're going to generate a key pair of a secret key and a public key. And they're going to secret share this secret key amongst themselves so that no individual party actually holds this key, but when they come back together, they'll be able to recreate it. And we're going to distribute this public key to all the devices. Now, all these devices can take this public key, and they can encrypt their data knowing that the aggregator doesn't actually have the secret key, so they won't be able to decrypt it. So they can send off their data with confidence to the aggregator, who will take all these ciphertexts and aggregate them all up. So at this point, we have one encrypted sum, which the aggregator is holding, and they don't actually know what the value underlying here is. It just looks like gibberish to them. And so to actually get at this data, they're going to have to communicate with this committee. And what they're going to do is they're going to send this encrypted sum along with a guess from the previous round of this. And the committee is going to recombine the secret key, and they're going to do a few things here. First, they're going to add some noise to the sum. So this is going to give us our actual differentially private guarantee. They're going to decrypt, and they're going to compare to the guess and release the final answer only if the guess was not close to the value they observed, or this noisy value. And a large amount of the time, they might just send a confirmation that the guess was the same. So notice here that we're only adding this differentially private noise once, right before we release the data. And so what that lets us do is it gets a much better privacy accuracy trade-off. So we're getting great accuracy here by only adding the data once and not at every device level. And we're maintaining privacy through this differential private guarantee, as well as making sure that all the data is encrypted until we do that. So this has been a high-level overview, and now I'm going to tell you about a few technical details of our system design as well as our evaluation. So first of all, our threat model. So we want to protect against an aggregator who may want to learn as much about user data as they can. And we're modeling this as occasionally Byzantine. So aggregator can be, we want to protect against both internal malicious behavior, so that could be employees or also external attempts to get at the data. And in particular, we want not the aggregator to be malicious, say, at the beginning of the system because they may have to install this operating system onto devices. Now, we also want to protect against malicious devices. So we're going to assume that a small fraction of the users can be Byzantine. And this is useful because we're dealing with huge user bases. So if you look at Apple's number of devices out there, it's estimated to be 1.3 billion. So even 3% of devices is 39 million, which is more than known botnet sizes. So this lets us reason about things such as committee selection, which I'll talk a bit more about. And our goals are twofold. I've already mentioned them. What they be repeating is that we want accuracy. So aggregator learns the answer to their query with very little noise, and privacy. So the aggregator cannot learn the data of individual users. Now there's a few subtleties here that I'm going to get into about how do we actually protect against this threat model. So the first is coming with this key pair. So as I mentioned, users are encrypting with a public key. And the question is, who holds the secret key? So again, because of our Byzantine assumption, we can't rely on the aggregator because they could decrypt any individual's data as soon as they got it. Now, we could introduce an additional party, but it can be hard in practice to find a party that both everybody trusts and is powerful enough to handle this, so we'd like to avoid that assumption. And so the idea is we can distribute this among the devices that we already have. So we're going to use a random sortition method inspired by AlgoRand to generate a dynamic committee of devices. And it's very important that this is random, that the aggregator can't influence this, so that they can't just corrupt those group of devices. And it's also important that this is dynamic. So we're not just going to elect one group and let those be a target for corruption. We're going to re-elect a committee every round. So again, they're going to generate this key pair. And in doing this secret sharing of sharding the key, we're going to tolerate drop-off of devices. So devices may not be in line to recreate this key. And we're also going to use our assumption of malicious devices here. So we're going to guarantee that no malicious subset of devices can recreate this key on its own. And then finally, this public key is going to be signed by the committee and distributed to devices. And this is crucial because when devices are encrypting their data, they need to know that the secret key isn't in the wrong hands. Now, once we have these ciphertexts, there's still two challenges here that are a little bit subtle. So one is that actually users could input bad data. So if I was inputting only values between 0 and 1, and I just uploaded a value of 1,000,000, I could completely mess up the aggregator's results. So for this, we require users to submit a small zero-knowledge range proof that just proves that their value is in a certain range. And we also want to protect against the aggregator not summing up data correctly, so in order to target specific individuals. And I'm going to focus on this. So one thing the aggregator could do is multiply the data by a large factor, such as 1,000 here. So I'm going to percolate this across. So instead of 0.9, this now becomes 900 and 100. And this also is included in the sum. And differential privacy is designed, again, to protect individual users, but still report aggregate trends. So if we multiply one user's data by more than, say, the size of the entire user base, the amount of noise does very little to obfuscate this individual information. So to solve this, Honeycrisp requires what we call a summation tree. And the leaf nodes are going to be the individual data points. Every parent interior node is going to be the sum of its children. And the root node is going to be the total sum. So all these values are going to be encrypted. And we're going to require devices to randomly select triples of nodes to enforce this correctness. So they're going to select here a parent and two children. They're going to check that indeed 0.9 plus 0.7 equals 1.6, and do so for all of the triples. And by distributing this among devices, we ensure that devices don't have to check too many things, but we still enforce correctness. Here's an example of when things go wrong, and this 900 value is inserted there. These checks will indeed succeed, but we see that 0.9 plus 0.7 is not 900. So in this case, we raise an alarm, and when the alarm is sounded, the protocol will stop to avoid any access of private data. So I've talked about the goals of our system, and these are the formal guarantees we show in the paper. I'm not going to get into them. I'm just going to say that correctness is not satisfied when the aggregator is malicious, but privacy will hold always. And we also guarantee that the system continues to function, so can be queried, and that users cannot raise that alarm without proper cause. And these proofs are in the paper. So now in the last couple minutes, I'm going to talk about our evaluation. And there were a lot of different questions that we are trying to answer in our paper, and I encourage you to check that out if you are curious. But I'm going to talk about a few of them here. The first is we wanted to see whether we could give stronger guarantees for a long time. So on this x-axis, I have the number of years that the systems could run before depleting privacy budget, and this is on a log scale. And the y-axis is the privacy budget consumed. And we're looking at, in particular, word frequency data from Twitter to see how often words frequency was changing. And one thing that we care about is this golden epsilon equals 1 line, which is a commonly recommended privacy budget. So ideally, once we hit this line, we should stop issuing queries. So we're going to compare two systems. The first is a baseline system, and this is an implementation based on Apple's description of their differentially private system. And this is configured to be less aggressive than Apple's system, which is why we see that this lasts for 91 days. So at the point of this intersection, which is what we care about, that's when the system should stop. And now we'll also compare with Honeycrisp system. And so this is our line. And so there might be 2 points here that you care about. The first one is this point where it seems like Honeycrisp is above the baseline. And that's just because we're prepaying for a disclosure up front. What we really care about is just the worst case privacy loss. And that's when we intersect this golden line, which is actually over 10 years. So we can run the system for over 10 years with a good privacy budget and gather accurate trends without ever leaking more data than we should. Now, I'm going to run through this quickly. We also wanted to see that since so many relevant companies have such large deployments, can they handle the scale? And this is the number, again, from Apple's deployment of 1.3 billion devices. And what we found in short is, yes, it does scale. So here's the numbers we're looking at. This is the 1.3 billion, and we also looked at values a factor of 10 and higher and lower. And so we see that this scales to billions with just this 1.2 megabyte costs for users. And of course, committee members do have to do more in the random tiny fraction they're selected. But the reason this is so low is that most of the heavy lifting is done by the aggregator. So the same bandwidth cost will essentially scale linear with the aggregator. So I'm just going to leave you with this summary. So distributed analytics is hard. There's often these difficult choices between privacy and accuracy that in practice heavily favor accuracy. And our contribution uses the sparse vector technique as well as this architecture of homomorphic encryption and secret sharing within a committee to give us both strong privacy and good accuracy that scales to billions of devices for a 10-year period. So happy to take any questions.
Questions?
Hi.
Hi.
A question about the sparse vector theory. There was this idea that you said that if I keep asking someone the same question, the answer hasn't changed.
Right.
There's no privacy violation. But I'm not sure that I buy that, right? I could ask you a question like, well, I'm not going to ask you a sensitive question. I could,
Sure.
right? And you'd say, no, I haven't done anything illegal, right? I'm going to ask you again, have you done anything illegal, right? And you say no, right? So assuming that we both agree that you don't lie, it does sort of reduce your privacy in a way because I know that you haven't, right? And the answer hasn't changed, right? How many children have you got? 0. Has the answer changed? No. Especially if I know something about you, like you're not married. So if the answer has changed, right? How many children have you got? 1. So I'm not sure I understand the privacy implication of that.
All right. Yeah, so you're absolutely right. And so actually what the sparse, so I've given a small simplification here. And what the sparse vector theorem actually states is it reasons about the ways that the different queries compose on top of each other. And it gives us this formula that we can see based on how many times I asked a query and based on how many times the data changes. And so you can mostly think about it as when the data is changing, that's kind of, I'm paying logarithmically versus a linear when I'm getting a precise answer. So this is something that you're right, that we have to reason very carefully about what is the actual privacy loss. And so that's the reason why in this graph that I showed here, we kind of see that on this log scale, ours is kind of scaling linearly on this log scale, and theirs is exponential because we are essentially doing this logarithmically. It's just kind of intuitively easier to think about this as not paying, but you're right that we are paying something for it.
Is the guarantees of these two ideas, differential privacy and this new idea, is this equivalent guarantee?
Yes, so this is exactly differential privacy, and sparse vector theorem is a theorem that comes from the theoretical differential privacy literature. So this is the exact same, when we say epsilon equals 1, that's the exact same guarantee. Mm-hmm. So this is just, we're calculating this in a slightly different way, and in particular, lets us leverage this fact about you don't pay as much when you get the same answer to the guess. So thank you.
All right, thank you.
Hi, nice talk, thanks. Is there any requirement on the number, on the dictionary you track when you count stuff? Is there any requirement on like imagine new words or invented regularly? How does it impact?
Yeah, so there's no requirements. So presumably this could be used for whatever the kind of queries that the aggregator is asking, but we are supporting just additive queries. So if you want to do something that's not additive, that's not supported, but we actually find this is enough to support, say, the queries that Apple is asking in practice. But yeah.
Cool, thanks.
We have just a little time. I wanted to ask one last question, if I could. I wanted to ask, you mentioned when you talked about the evaluation at scale, that the committee members have some more work to do. Could you tell us a little bit more about that in terms of as you scale up, how much work there is for the committee members?
Right. Yes. So the committee members, the overhead that they have, that also doesn't scale really too much, or it really doesn't scale with the number of users. but it is a more involved cost. So they might have to perform something like a few 3 gigabytes of communication and computation of 5 minutes, including some waiting to do the multi-party computation. But this isn't actually going to scale with the number of users. So we test different values from around 20 to 40, and these are kind of the feasible things we can do with the current implementations of multi-party computation. But yeah. All right, thank you.
Let's thank the speaker.